So here we will look for something actually quite interesting in terms of the kind of results that we can get with this algorithm. Okay. So again we will only consider initially fixed capacity service centers and delay centers. Okay. So this algorithm is now considers right now only these two. Right. So basically single server queues or infinite server queues, one or infinity, nothing else in between. So this result goes back to 1967 from Gordon-Newell theorem. Out of that distribution of the number of jobs in a queuing network. Okay. So the theorem basically states as follows, right. So given again a set of queues, right, given a with exponential service times etc. Then let n denote this vector, right. So this denotes n denotes the number of at a given instant of time there are n1 customers in Q1 or n1 jobs in Q1, n2 jobs in Q2 and nm jobs in Q1, right. This is the number of, so ni is the number of jobs in device or Qi, right, at some instant of time. So then the probability that, so what is the probability that for some given n, right, and a given system, this is turns out to be simply so it is proportional to the, it is equal to the product of each demand raised to the corresponding value of n. So d1 raised to the power n1, d2 power n2 and so on, dm to the power nm. Unfortunately I am not proving that, the book skipped the proof, I went and looked at, we can go back and look at the original paper for the proof, but we may sit here for, right. So we are only looking at the result here because it is convenient. Okay. So now I have, so now we remember in the case of MM1, right, what is the state of the system, what did you model the state of the system, simply the number of customers, and once I know my PIs, right, I could compute everything else based on that with Little's law and so on. So likewise now I have this probability with which I can now compute many other things in the system, right. So this is the probability of having at a given point in time these many customers in each of these queues, and it is just proportional to d, which is d again is equal to v into s, right, di equals vi into si, that is what we saw defined last time. D is the demand, yeah, okay. So we will write this, first I put something n, right, so n is simply the total number of customers in the system like we always had, and then di is the demand made on device I, which we have defined so far as Vi and Sm. If you look at other definitions, they will use either Ei as visit ratio, right, divided by mu I, because it is exponential, 1 over mu I is your service time, right. So we simply
we have the relation as rho. The D is almost equivalent to that rho, because
there is also a normalizing factor. So there if you look at it will be simply 1 minus rho into rho 1 to the n, right. So where rho is basically lambda by mu, right. So and but here that there lambda is the arrival rate, here that lambda is sort of like your visit count to the system, right. If there is a tandem queue, we saw that it is simply product of, right, of the individual queues. It is something similar to that, and then there is this normalizing constant because of the fact that d and n, d can be very large, right, d can be any number, it is not constrained by, in the case of MM1 we said rho is less than 1, so we know that we can always compute that, right, whereas d is very large, to compute this becomes a problem, right. If d is 1000, then 1000 to the power n is also very large, you start looking at very large numbers, right, then your system starts running into either overflow or underflow errors. If d is very small, you run into underflow errors, if d is very large, you run into overflow errors, especially for large values of n, but this is the formula, right, this is proved, and so now I can use this to, right, figure out certain things, okay. So then I have defined my g of n, so g of n is a normalizing constant. I need this to ensure that all the probabilities are summing up to 1, right, and that they are all less than or equal to 1. So this is simply sigma over all possible values of n, right, every combination of n So to avoid this computation problem, we can look at two ways, right. If d is very large, then but the good thing is the d's are again appearing in the denominator, right, so I can simply scale the d's to whatever value that I want, right. So one way to reduce the computation, right, to reduce the computation errors, right, overflow etc. I will simply choose select, right, some scaling factor alpha, alpha usually less than 1, right, and then rewrite or of course if the d's are very small then you will scale them up, right, so it depends, right, if all d's are right are all greater than 1, you want to scale it to some number less than 1, right, and if it is too small then scale it up appropriately. For example, s in a service time, right, in a gigabit net system your packet transmission time will be order of nanoseconds, so VISI will be very small, and then you are trying to, in that case you want to just scale it up to right some multiple. So we now express everything in terms of this yi is nothing but alpha into di, okay, and alpha can be anything, you can just pick the largest value of d, whatever it is. This is even if it is not greater than 1, you can still use that for in some situations, but anyway. Or if you want to just normalize everything to integers also, you can try to do that if things are nicely set up as multiples of integers, okay. So for example alpha, I can use this so called d average, I can use that, right, or I may just say that I will scale everything with respect to d max, so d max goes to 1 and everything else is less than 1, so something of that sort, or any other arbitrary value, right. So then now my p of n, which is the same expression that we saw before, is nothing but so instead of expressing it in terms of g of d, we are expressing it in terms of y, questions? Alright. So now let us go back to our the same system with the queue, right, one CPU, 2 disks, closed network, okay, and let us assume that SCPU is 39 milliseconds, SA is 180, SB is 260 seconds, and then vCPU is again given to you, okay. So your dCPU is now, this is in milliseconds, so we will just put everything in seconds. dA is 2.34, so everywhere there is some 13 hiding, right. So let alpha be 0.78. So therefore yCPU equals 1, ya equals 3, yb equals 2, right. Ya is alpha di, so divide everything by 0.78, you get it. Yi equals, no, I am sorry, one over 0.78, this is what happens. Correct or not? Okay. So now let us assume that there are, this is a closed network, right. So let us say that there are a total of 3 jobs in the system, and that is all I am considering, right. Closed network with 3 jobs. So what is the probability of, right, certain number, like 1 job in this queue, 2 in the other queue, and so on. So because there are 3 jobs, there would have been, assume that there is no terminal here, there is no thinking time, so z equals 0, okay. So there is no terminal at all, it is just these 3 queues, these jobs are just switching between these 3 queues, right, okay. So now I can enumerate, right, if I want to find out, so what is the probability, what are the different ways in which these 3 jobs can be distributed among these 3 queues, what is that. So what are the total number of, what are the total combinations for this n, right. I said n is the set of all possible, right, state combinations, 4C2, okay, so that equals 4C2, 3 jobs 3 queues, 3 jobs 3 queues won't be 4C2. So I have 3 jobs distributed among 3 queues, right. So what is the combinatorics, didn't you get this, look at it somewhere, right. So the number of possible states so I have n objects, right, that can be in m queues, that can be distributed among m queues. So what is the number of ways in which you can do that? 5C2, okay, good. So how did you get that?
Put two partitions in
Okay.
3 plus 2 C.
So that is basically, can you give that to me in terms of n and m?
Plus n minus 1 C. N minus 5 plus
Or of course n, right? M minus 1, if it is easier if you think about in terms of the partitions, right. So this is the number of ways in which number of possible states. And yeah, so if I guess I found this explanation. So if you represent your set of jobs as dots, right, so this is the n dots that you have, right, and then you are basically partitioning this into m sets, right. You can put, so basically have bars to represent your boxes. I have m minus 1 boxes, right, so I can put, let us say m equals 2, right, or m equals 3 in our case. I need to draw 3 bars, right, to basically split. I have in this case n equals 8 and m equals 3, right. So now I have to look at these 2 bars, and so where I can place them, I can place them in, right, any one of these. So it is n plus m minus 1 positions are there, right, I can, and then you have m minus 1 choices, or so you have to select m minus 1 positions out of the n plus m minus 1 positions possible. So that is how we get that. Okay, that you can check it out later, right, just take this for granted. So there are, so these many combinations. Okay, so what is this of the order of, what is the order complexity for this? So if you have to compute this, right, this many states, the number of states is how much? The order of n to the power m minus 1, so, or n to the power m, that many states are there. That again you can verify. So in our example, right, for n equals 3, m equals 3, possible states this is 10. So you have to enumerate 10 possible states. Okay. Why do I have to enumerate all 10? Because I have to compute g of n, right? G of n is the summation of over all n, which is the yi to the power ni. So I basically have to have one big table that actually does that. Okay. So let us compute some parts of this table. Okay. So this is the number of items in the CPU, number of items in disk A, number of items in disk B. Okay. And right, this is your yi's that we are sorry, yi's we already known. So this is this, and then right, for this combination we can look at the so for every combination I have to go and figure out this yi to the power ni, right, and yi's we figure out to be 1, 3 and 2. So when this is one possible distribution, right, all the 3 jobs are in the disk B. So what is the corresponding product here? 8, and we can just do this for the rest of this class, but then I put 0 here, 1 2 0 2 1, then I have 0 3 0. Okay, and this is now 3 to the power 1 2 squared, this is 3 to the power 2 9 into 2 18, yeah, and so forth until we look at the final combination is 3 0 0, because the fact y1 equals 1, this just sums up to be 1. Okay. So remember my g of n is summation of all this yi, which is 90. once I compute g of n, then my formula says, right, p of n equals this product divided by g of n. So what is this? This is 8 by 90, that equals 0.089, this is 12 by 90 and so forth. Dot dot dot. So that is how I compute the PI. So given a system, I have to go back, write a small program to do this, right, only worrying about overflow or underflow, but I can do that. I am sorry? No, the alpha does not come in this picture because alpha is already in the denominator and the numerator. Yi is reduced and likewise so both numerator and denominator are both reduced by alpha. Right. So you do not need to reduce this further. We use alpha later on when we come to the actual through metrics, we will have to use alpha to scale it back to the original values. Okay. So that is one way of computing, right. There is another way of computing g of n m. Do you know what that is? So given n and m, we can compute g and m faster. So okay, let us do that. So let g and k is defined this way, then we can actually prove this, but I will keep that for some other time because you got to get moving. So the number, okay, so your g and k, right, so g and k, this is a right expression that ties up these two. So this simply says that in the particular qk that you are looking at, there is no job. So all the n jobs are sitting in the k minus 1 queues, right, there is one tagged qk that you are looking at. So it is either all the jobs are in the other queues k minus 1 queues, or there is one job which is this yk, and then the remaining n minus 1 jobs are still across all the k queues, right. So one of those jobs you are looking at putting them in this queue. So there is just one job you are tagging, and then that is either in this kth queue or not in this kth queue, and this is the probability. Okay, so this is your g. So why this is useful is now I can actually compute my g of n's much faster, right, with the simple set of multiplications and additions. Okay, so now let us define some boundary conditions, right. So what is g of n comma 0 equal to? How many ways can you distribute n objects in 0 queues? No, 0. So this is boundary. And then how many ways can you distribute 0 objects in k queues? Exactly one way, right, all 0 for all k equals 1 to m. So now we construct a table with n plus 1 rows and technically m plus 1 columns, but you do not have to worry about that. M columns, and proof is there in the book, right, how we can do this grouping for a simple three 3Q 3 customer case you can actually come up with it. Let us not go there. Okay. So now my table essentially looks like this. And this is basically so they are assume that the table has these row values. Okay. So the number of ways of distributing 0 jobs, right. So we said that 0, this is 1, and then so we will initialize these two initial the first row and the first column. This is y1. Okay. So there is only one queue, right. The first column simply says there is only one queue and there are n elements. So therefore all for all ni, right, the corresponding will simply yi to the power ni. There is no other queue to be considered in the system, right. That is your, these are your initial conditions, right. We know that 0 customers in n queues, whatever be the number of queues is the probabilities g of n, right, g is 1, and if there is only one queue it is simply y1 raised to the power n1. So that is how these two columns are generated. So now we just simply use our previous expression, right. So you look at the, it is yeah, so let us look at some, so there is yk here, right, this is your kth column, that is also 1. So what do you have? You have g, this is the nth row, right. So your g nk minus 1 comes from your previous column, and then you have g n minus 1k from your previous row, right, and this is simply so how many computations now? Nm, right. Then every computation is simply an addition and a multiplication. So that is how I can build my, this is I think Boozen's algorithm, and then finally you compute g. So without having to enumerate, you simply have nm computations. In the previous case you have to do all the n plus m minus 1, choose n options. Now you do not have to do that, you can just compute this way, right. So you fill up this one, then you can fill up this one, so you can fill row by row. So as you go along, g of 1 or g of 1 comma m, right, g of 2 comma m, everything is getting generated. And we also will find that g n minus 1 is also, right, this g n m is basically what we are looking for, g of n, right.
So g n minus 1k, what will be the value? Y n minus 1 to the power.
So this will be y1 plus y2 here.
But it will be y n minus 1 to the power k.
Not power, simply this is y1 plus y2, 1 into y2 plus y1, this will be, it is, this simply comes as it is, only the one coming above is gets multiplied by another value of yk. That makes sense, right, because you are multiplying, you are raising things to the power, so your yk is getting added. Okay. So we will have one more step and then we will go to that axiom that people wanted. Okay. So can you compute this for n equals 3? m equals 3. Since this is 1, this is very simple, right? So 1 plus 4 into 3, 13, 13 plus 6 into 2, 25, then 1 plus 39 is 40, 40 plus 50, 90. So in the process we also computed what if 2 jobs are placed in 3 queues, okay, the GF2 is basically 25, and 1 job placed in 3 queues also is simply 6 different ways of doing that, or the GFN is basically 6. Okay. So we will come back next class and look at actually how we can derive some of the terms, but since there was a request to see whether the axiom runs or not, so next 20 minutes I am going to just check out the axiom and hopefully it runs, right, otherwise I am, so just as a right teaser, so if I want to find out the utilization of Qi, that is simply given by we can derive this from one known expression, right. So for example, so if I am looking at the CPU, utilization of the CPU is how much, Yi is 1, right, and Gn minus 1 is 25, 25 by 90. So that is your uCPU. We can go back and check with the MVA if you want the other calculation. So essentially everything gets proportional to di and this ratio of Gn minus 1 to Gn, all the Q utilizations. So once you get U, then you can compute other things, right. Then Si can compute, which is Si by 1 minus Ui, right, and so on.